let's just look at a signal, something like this. X of n is negative 0.8 to the n times u of n plus 2 minus u of n minus 5. Now, we all know what that looks like. It starts at negative 2 and ends at what? Be careful. Where? Let's see. It's, I want to be doing the calculations, and it's decaying as you go to the right, so it's growing as you go to the left. So it starts at negative 2, 1, 2, 3, 4, stops. Right? Don't remember that little trick? Because u of n plus 5 kicks in at time 5 and drops it back to 0 there, so it ends one sample before that. Now, let's see if y'all got this copied down. I should have written to the side because I'm going to lower the screen. You be doing that, and I'll be getting MATLAB started. If I got it written down. So, all right. Now we cover it up. And let's see how we can generate something like that with MATLAB. There are a couple of things that I'm going to have to show you. Some of them we may have talked about in 431, so if I bore you, tell me, go on. And if you need more explanation, then slow me down, ask me to repeat. Okay, in MATLAB, I am going to generate, let's say I'd like to plot that signal from negative 10 to positive 10. So I'm going to generate a vector, n equals negative 10 colon positive 10. And you remember if I put a semicolon at the end, it'll suppress the echo, but I want to show you what we've got. Okay, negative 10, negative 9. By the way, you can, if you wanted to create a time vector that is continuous time, you can, the format here is start point, end point. The general format, though, and we don't need it right now, but we might at some point, what I just did is n is negative 10 to 10. The general format, though, is n is start, colon, increment, colon, end. But if I only give it 2 parameters there, one of them's missing. It says, oh, those 2 numbers must be the start and end, and the increment's 1. So if you give it 3 arguments, I could have given it negative 10 colon 0.1 colon 10, and then it would have gone negative 10, negative 9.9, negative 9.8. Okay, if you just give it 2 arguments, and that's convenient because integers is what we need for our time index in this class. So now I've got my n variable, and I am going to write x equals, let's say x1 equals, yeah, I did start early, Juan. X1 is negative 0.8. Now, I want to raise that to the power. Negative 0.8 to the negative 10, then to the negative 9, then to the negative 8. So, raising to a power, you know, is this symbol, and don't write it yet. Raise it to a power. The problem is that n vector is a vector, and the mathematical operation of raising it to raising anything to a vector power is undefined. So the MATLAB programmers included another command, which means raise point by point what we're doing. Raise it to the negative 10th power, then to that negative 0.8, the negative 10, then negative 9, then negative 8, then negative 7, and that is called point to the power. okay? Mathematically, and you've been in a lot of math classes, mathematicians would faint if you tried to raise something to a vector power. There is no such operation. But in DSP, that's something we do all the time. So they included this point to the power n. And I want to show you, now this is not my final answer, right? All it does is the exponential part of it. And that's why I call it x1. Now, stem n comma x1, I get my x-axis variable and then my y-axis variable, and a stem plot goes like this. Okay, let's blow it up. Does that look like what we were expecting? I said, the easy place to start is at 0, it better be 1. 1, and then it's growing and oscillating as you go to the left, and oscillating and decaying as you go to the right. Okay? And everything's good except for those step functions. Okay? I'm going to create that. I'm going to give it another name. Let's say x2. x2 equals, let's see, Haley, are you the only computer engineer in here? Well, all of you have had some programming classes, and all of you have had digital logic, because I'm going to have to use some logic operations here. And MATLAB incorporates logic operations into the software very well. X2 is, and just because I tend to be very conservative here, I'm probably using more parentheses than I need. But you know, when you do operations and you want to make sure the order of precedence is right, you throw in more parentheses. So, what I'm going to do is x2 equals, let's see how to do this, 2 parentheses, n greater than or equal to -2, and n less than 5. Okay. And I'm going to leave out the semicolon. Whoop, wait a minute, did I leave out a, oh yeah. Y'all didn't catch that for me. N less than 5. Yeah, okay. What? Logical scalar. Hold on a second, this was supposed to work. First time I knew what the error was. Logical operations, n greater than or equal. Okay, this is not a some kind of a typo or a syntax error. This is something I've always done. And let's see. Or and operators must be convertible. And less than. Bear with me just a minute, because there's something that I am Has anybody used this before? Anybody tell me what to do with this? I mean, do you see any problem with that? I've done it many times, and something is just, I'm just drawing a blank on it because, let's see, let's say just n greater than equal to -2. Okay, there's what I'm trying to do. Y'all see that? N is greater than or equal to -2. -10, 9, 8, 7, 6, 5, 4, 3, starts at -2. Okay, what about
Can you try changing to one and off of
one,
it?
the ampersand there? Okay, let me I'll stop. That's why you're the computer engineer. Google, thank you. Okay, yeah, all right. So now, let's see what I've got. -10, 9, 8, 7, 6, 5, 4, 3, -2, -1, 0, 1, 2, 3, 4. That's what it is, right? Thank you. That's exactly what I was looking for. I thought it was a double ampersand.
Well, in code it is, but I guess from that way.
Done in MATLAB. Okay, yeah, all right. So, here's what we're going to do now. X equals x1. Now, what I want to do is multiply those vectors point by point. Again, that is a mathematically ill-defined operation. So it's x1 point times x2. And then stem x, n comma x. And what we should have is the same thing. -2, -1, 0, 1, 2, 3, 4. Yes?
So, on the one that you drew on the board, it stopped at 4, correct?
Correct.
Now, why does this one stop at 4 when you used 4, but on that one you used 5?
Oh, good question. Let me show you. What I should have done in less than 5. Now that would work.
It'd be the same thing?
Yes, give you the same thing.
Okay.
I had it set up that way the first time, and then because it was giving me errors, I said something's wrong, and I was trying to make sure that wasn't the problem. All right, yes, same thing. But remember that the n minus 5 minus u of n minus 5 makes that one kick in at 5, which drops it down at 4. 4 is the last non-zero term. Do you want me to draw that up here?
I just don't understand why wouldn't 5 be the last non-zero term?
Okay. U of n plus 2. I know this one's not your question, but that one goes on forever.
Right.
U of n minus 5 goes 0, 0, 1, 2, 3, 4. Jumps up at 5. Goes on. So 1, 2, 3, 4. Right there.
Okay.
Drops back down.
Okay.
Yeah, I totally understand. I've been through this many times. Went through it myself. Okay? Now y'all see how to change those. And by the way, when you plot, then when you do a stem plot of a signal, you'll need to do the n first. Otherwise, watch what happens if I do this, just stem x. If you leave off the x-axis variable, the stem, or the plot for MATLAB plots it versus index of the array. And x is an array, and x is indexed as x of 1, x of 2, x of 3, and in this case, because it had 20, it'd go all the way to x at 21. Is that what it's drawing? Yeah, it starts at 1, 2, 3, 4, 5. So if you don't tell it, if you just say stem of x, it says, okay, I need to plot x. What am I going to plot it versus? It didn't tell me. And therefore, I just plot it versus the index. 1, 2, 3, 4, 5 up through 21. when you do stem n comma x, well, n went from -10, -9, -8 through 10. By the way, that is 21 points, isn't it? -10 to +10. You count -10 to -1, 1 to 10, that's 20. The 0th is 1, is another one, 21. So then it plots, okay, -10, -9, and then you plot the numbers here. Okay. Good? Yes?
No, because I'm kind of missing the finer point between stem x and stem nx. Because it's still plotting 21 both times, right?
It is. But what it plots on this axis, if you don't tell it what to plot on the on the horizontal axis, it just plots x, which is a bunch of zeros, and then some of these, and then a bunch of zeros, and it plots them. If you don't tell it what goes on this axis, it just starts at 1, 2, 3, 4. And that's what we have up there. As opposed to, right, 0 through, well, it just put in 0 because it always starts at 0, but the index is 1. As opposed to what I had done before, which is stem n comma x, and now you can see that it will have the x-axis has got the right n values. Starts at -10. Okay? We're going to get into the FFT in another week or so, and that's going to be crucial to us to pay attention to that horizontal axis, because it's going to be the frequency axis. Okay, was that what I had promised to tell you all and had left out? And do you say that I had not given you homework number 2? Okay, I thought I had. But regardless, you can start on 3 anyway. We good with this? After like 3 lectures of promising, now I finally have kept my promise. And so, I will, at this point, turn that off. Raise that screen. And start talking about some more little tricks with the Z-transform. Last time I did talk about, what was that subject? Difference equations, recursive, non-recursive, and pole zero plots, and stability and causality. I did a lot last week, no wonder I was tired. This time, we have talked about some inverse Z-transforms, but I'm going to show you a few more tricks that you'll need, and homework number 3, you'll need them all. If I were to write x of z is z over z minus 1 and z minus 1/2, you know that we would partial fraction expand like this. Az over z minus 1, bz over z minus 1/2. And A and B could be found by the cover-up method, right?
Yep.
So A would be 1 over z minus 1/2 evaluated at z equals 1. Why do I not have, obviously I covered up the z minus 1 term. Why do I not have a z in the numerator? Where did it go? I pulled it out. Yeah, I pulled that z out front, and then I put it back in here and here. So that is 1 over 1 minus half, looks like 2, and B would be 1 over z minus 1, evaluated at z is 1/2. -2. So the answer looks like x of n is 2 u of n minus 2 times 1/2 to the n u of n. Okay, there's our final answer. Now, I'm going to go into some sneaky little algebraic tricks that we're going to play so that we can avoid doing any real work. That's a good thing, right? did I also talk about residue Z last week? Yes, I did, because we were doing complex poles, and I showed you how to do expanding complex poles, right? 2 magnitude of A, R to the N, cosine, yes, very good. Okay, but what if, now I'm going to take that one example right there and see if I can't get a lot of mileage out of it, okay? And you say, but this is, what if it's something different? Well, the idea is the same. What if I have x of z is just 1, z minus 1, z minus 1/2. And let's say we've already done that problem, and we have already done that problem. We're not lying. We've already done that problem, and let's see how many questions we can answer without redoing any partial fractions and without doing any other real work. What's the difference between this one and that one? Don't have z in the numerator. If I were to put a z in the numerator, would you know the answer? But there it is. Can I put a z in the numerator? Yes, if I put a z to minus 1 out front, right? What's z to minus 1? What operator is that? Delay? Delay by 1? So in this case it's 2u of n minus 1 minus 2 times 1/2 to the n minus 1 u of n minus 1. And so we found out how to handle that one. So if you don't have a z up there and you'd like to have a z up there, put it in. Just put z minus 1 out front, and the z minus 1 is just a delay. No partial fractions involved, right? No more. All right, what if instead of that, it was z to the 10th over z minus 1 times z minus 1/2? Now, by the way, I've been assuming over here that the ROC is magnitude of z greater than 1, right? Didn't I? Y'all remember, if it converges outside the poles, you've got a right-handed sequence and vice versa. Well, this one, it turns out the ROC could not be bigger than 1. It would have to be 1 less than magnitude of z less than infinity. Do you see this one can't converge at infinity? Will never converge at infinity. Why? Power up here is 10, power down here is 2. Okay, and z to the 10th over z squared minus something down here, this will never converge at infinity. Is that obvious? Do L'Hopital's rule in your mind. Okay, I am going to make this point. If you all say you don't see that, I want to prove it to you. Infinity over infinity, what do we do? Take the derivative? What do you get? 10z to the 9 over 2z. Still infinity over infinity? What do you do? Derivative again, 90z to the 8th over 2. Now let it go to infinity. What do you get? Infinity. Right. There is no way. That one cannot converge at infinity. And I'm going to show you what the implication is shortly. Do you want to do, oh, by the way, you can't do a partial fraction expansion on that. You cannot do it. Why? Numerator order, higher than denominator order. But can we do this? Z to the 9th, z over z minus 1, and z minus 1/2 over 2. Right? Can we do that? What is z to the 9th? If z minus 1 is a delay by 1, this is an advance by 9, which means the answer is 2u of n plus 9 minus 2 times 1/2 to the n plus 9 u of n plus 9. Okay? Does that have anything to do with that ROC? where does this signal start? At what time? Signal starts at time -9.
Yeah.
At -9, and then it does whatever it does. I don't know what it is. Non-causal? Why does it start at -9? Because of the term z to the 9th, right? And I said that term, the fact that this was z to the 10th, and that's where that z to the 9th came from, that was why it couldn't converge at infinity. What do you know about infinity? If it doesn't converge at infinity, it's not. If it doesn't converge at infinity, it is not causal. Is it not causal? It's not causal. Yeah. And that whole thing about the z to the 10th, which gave you the z to the 9th term, and couldn't converge at infinity, that's also why the sequence starts at -9. It's a non-causal sequence, specifically because of that advance by 9. Okay? So, all right, what about something, let's see, what about this? Z squared plus 1 over z minus 1 and z minus 1/2. This one's going to create a little bit of a problem, isn't it? Notice you've got a z squared up there, and then but then you've got a constant. You can't factor out a z there, agree? What are we going to do in a case like this? We're going to do something that seems a little weird, and it's going to lead to a long answer, but at least we won't have to do partial fractions again. I'm going to write this as z over z minus 1, z minus 1/2, plus z to the minus 1, z over z minus 1, and z minus 1/2. Now I've got 2. So I went from one expression to 2 expressions, but I know the answer now, don't I? What have I got? A z, that's an advance by 1, so it is 2u of n plus 1, yeah, minus 2 times 1/2, n plus 1, u of n plus 1, plus, what about this one? It's got a delay. 2u of n minus 1 minus 2, 1/2 to the n minus 1 u of n minus 1. And you say, that's kind of complicated. And my response is, yes, but at least we didn't have to do partial fractions again. We're trying to see how many answers we can get without having to go through that partial fraction expansion over there. And I think that's about all we can get. Right? So those are the kind of tricks that you need to play on homework number 3. And then, so let me just pick a couple of random problems, because I spent a lot of time, it must have been 10 years ago, making out that homework assignment. It'd be a pity to have to make up new problems. So if I were to, I'm looking at problem number 2, z minus 4 over z squared, z minus 4 over z squared minus 0.64, magnitude of z greater than 0.8. And each one, I'm actually not joking about spending a lot of time at some point making those out, because each one of those problems is designed to make a particular point. Can you factor that denominator? I bet you can. Z plus 0.8. And by the way, if you have trouble factoring, always look at what the region of convergence is. Why would it be magnitude of z greater than 0.8? There must be a pole at 0.8 or negative 0.8. Guess what? There's one in both places. So, what are we going to do? Now, can we factor a z out of the numerator up there? Out of the whole number? No, we're gonna do it just like that,
Yeah.
right? I'm gonna write this as z over z minus 0.8 and z plus 0.8, and then minus 4, z to the minus 1, z over z minus 0.8, and z plus 0.8. And it's converging outside the poles, agreed? The poles are at plus or minus 0.8. And I am going to partial fraction expand just the first term. That is az over z minus 0.8 plus bz over z plus 0.8. And just real quickly, I'm going to find a and b. A is 1 over z plus 0.8, evaluated at z is 0.8. 1 over 1.6, what is that? 1 over 1.6, 5 over 8? .6 is 8 over 5, isn't it?
Why is it 1 over?
There,
Wouldn't be z.
took z out.
Yeah.
Gonna put z back in to this.
Yeah.
Okay. Whatever, it's 1 over 1.6. B is 1 over z minus 0.8, evaluated at z is negative 0.8, which is negative 1 over 1.6. Okay. So this is convenient because all the partial fraction coefficients are 1 over 1.6. So here you go. X of z. No, not x of z, x of n. We can go all the way to the time sequence. It would be 1 over 1.6 z over z minus 0.8 minus z over z plus 0.8. Okay, that's all that stuff over there. You with me? So I'm going to factor out that 1 over 1.6. All right, what do we get right here? 0.8 to the n u of n? Okay, 0.8 to the n u of n. Next one is minus negative 0.8 to the n u of n. Now, I'm done with the first term, by the way. Is that what we just did? Am I writing too fast, going too fast? Being too boring? Can't help that. So far, so good? Now watch what I do with the second term. All right, that's all of that. Minus 4, and then 1 over 1.6. Minus 4. What's the difference between this term and that term? We've got a minus 4 z to the minus 1 out front. So minus 4, 1 over 1.6. And what's the z to the minus 1 do for us?
Advance.
Delay?
Delay.
Right? All right, so it is same thing as that. 0.8 n minus 1 u of n minus 1 minus negative 0.8 to the n minus 1 u of n minus 1. And you might say that's pretty ugly because it's a whole bunch of terms. And I say yes, but I only had to do one simple partial fraction expansion. And there's something else to be said for it. It's right. And the reason, that has a lot to do with why I do it this way. Spend some time getting the partial fraction expansion right, because you ain't going to have to do it but once. And if you get the first one right, the second one is very simple. Did you see what I did? The second part, once I got the first one done, that's this part right here. That gives you that answer right there. Multiply it by negative 4, delay everything by 1, and then you got the same answer. With me? All right, there's another one here that I want to do, and it is number 5. And the point here Well, you'll see. Z to the minus 1 over z squared minus 1.7z plus 0.72, and the ROC 0.8 less than magnitude of z less than 0.9. There's a couple of twists here. And again, what about factoring that denominator? Well, everybody can factor a quadratic. It may take you a minute. But I'll give you a hint. Why would the region of convergence be between 0.8 and 0.9? That must mean that there's a pole at radius 0.8. Could be positive 0.8 or negative 0.8. It's just at that radius. And there must be another pole at 0.9.
Dr. Vargas,
Go ahead.
can you go back to the
Oh, okay.
the previous one?
Yeah.
Just on the first term, 1 over 46
Uh-huh.
with 0 for A N
Uh-huh.
U N.
Okay.
The first one, yeah.
Okay.
So with the second one, minus 0.8 n, is that n minus 1 or n less 1 or?
N?
Yeah, n.
That's just n.
Okay,
Because
why
that
is
term
that?
was this one. And the only difference between this term and that you're all right with, right?
Yeah,
Okay, only difference between this term and this term is that there's a negative sign right there.
okay,
That's because that coefficient was negative.
yeah.
And this one is z minus negative 0.8, so it'll be negative 0.8 to the n u of n. What part of that don't you like?
I need to digest that.
Okay. It's, the form is z over z minus a, and it's a to the n u of n. And in the first case, a is 0.8. But in the second case, a is negative 0.8.
Okay.
So that gives you negative 0.8 to the n u of n.
But if that's so, okay. Yeah.
Got it?
Got it.
All right. Okay, good. So,
Just, yeah.
all right.
A little bit confused, yeah.
Okay.
Yes.
That's right now?
Yeah.
Okay, let's guess at something here. But first, got a z to the minus 1. Let's make that a z to the minus 2, so I'll have a z up there, right? Will that work? And honestly, in a lot of cases, I just kind of guess and then multiply it out and say, is that right? Well, it looks like 0.8 and 0.9, or negative 0.8 and negative 0.9, or some combination of those, look like poles. Let's try this. You remember when you factored in algebra, negative and positive gives you z minus and z minus? That's going way back there, but you all remember that rule. So let's see if z minus 0.8 and z minus 0.9 will work. Let's see, multiply them out. Z squared minus 0.8, z minus 0.9, z is minus 1.7, and negative 0.8 times negative 0.9 is positive 0.72? Yeah. These are not just random numbers I made up. So now we've got that, and the z to the minus 2, we know what to do with that, and we got a z up there, we're good. So I'm going to write this as z to the minus 2, az over z minus 0.8 plus bz over z minus 0.9. And I'm going to find those coefficients. I got my z minus 2 out front, so forget it. I factored this z out, so forget it. So it's just 1 over z minus 0.9 evaluated at z is 0.8. Negative 10. B is 1 over z minus 0.8 evaluated at z is 0.9. And I think that's positive 10. Okay. Can I erase this now?
Yes.
Okay. So, here's what I've got. Z to the minus 2, 10z over z minus 0.9, I'm changing the order, minus 10z over z minus 0.8. Oh, wait a minute, I almost made a big mistake. Let's do problem number 3 first. And you don't worry, I'm not changing the problem. Problem number 3 says it's the same, but the ROC is magnitude of z greater than 0.9. Okay, and by the way, the ROC doesn't affect the partial fraction expansion. Does not. Which means what we've done so far is all right. What do you get there? You get a x3 of n. 10z over z minus 0.9, what is it? And it's converging outside the poles. I'll get you started. 10. Z over z minus 0.9. Z over z minus 0.9 looks like 0.9 to the n. U of n, I'm cleverly leaving some space. Okay, what's the second one? I did the first one, you did the second one. 10.
0.8
0.8
to the end.
to the n, leaving space, u of n. And why did I leave that? Go ahead.
Should one of those be negative 10?
Yeah, it is.
So that you're doing A is the second one? Or not the second one?
This one turned out to be negative 10, and this one turned out to be positive 10, so I switched the order, so yeah. I got it there. It made sense when I thought of it.
No, it makes sense. I just-
Okay. Connor? Good? Okay. Why did I leave space there? Because what did I leave out? Z to the minus 2, which means all these n's become
Minus 2.
n minus 2, n minus 2, n minus 2, n minus 2. And it's all done.
It's gonna be different term. Because z minus 0.9 and z minus 0.8 is that have to be the same term that it go to the power of n minus 2.
Right. You have a specific question about it, or just?
Yeah, no.
Okay. Can we go, that was 3. Problem number 5 is the one I started with. Okay, 5. We have reduced that to x5 of z is z to the minus 2, 10z over z minus 0.9 minus 10z over z minus 0.8. And the only difference is that the ROC is 0.8 less than magnitude of z less than 0.9. Okay, that does not affect the partial fraction expansion, so we can still use that partial fraction expansion. But here's what it does affect. When you go back to the time domain, remember a to the n u of n gave you z over z minus a, magnitude of z outside a. Remember that one? Here's the one we talked about a little, but we haven't used much. Negative a to the n, u of negative n minus 1 is also z over z minus a, but magnitude of z inside the pole. Magnitude of Z less than magnitude of A. Okay, look at those two terms. And by the way, that Z minus 2 out front works the same way it did before. Look at those two terms. And when I point to a term, I want you to tell me whether the ROC is inside or outside. Where's the ROC? 0.8. Pole.
0.049.
This ROC is that donut. Okay. 0.8. Where's the ROC? You only get one of two words. Inside or outside?
Outside.
Outside? Are you all just shy? Because this should be obvious. Right there is 0.8, and right there is 0.9. And the ROC is shaded. Okay, what about the first one? Where's the ROC?
Outside. Or
Inside?
Inside.
Okay, inside there. So what does that mean? Let's take the 0.8. It's outside that pole, right? It's outside 0.8. And by the way, the pole at 0.8, it doesn't care about the pole at 0.9. It's either inside or outside the pole at 0.8. And the answer is it's outside. So you get negative 10 times 0.8 to the n, leave space, u of n. And so what do? Got Z minus 2 out front, what do? N minus 2. N minus 2, N minus 2. Okay. Notice that one, that's the same as what answer we got in the other part. Why? Because up here, the poles were there, and the ROC was out here. Was it inside or outside the pole at 0.8 in that case?
Inside.
The ROC
It's
is outside the pole? And as far as that pole at 0.8 is concerned, it doesn't care if it's in this donut or if it's outside everything. It's outside that pole. Okay, so, first one. It's inside the pole. Which one of these is it? Number 1, number 2? Which one's inside the pole? Magnitude C less than 0.9? You see that? Okay, so what does it say? I've got a negative, so there's a negative 10. And then a to the n, so it's 0.9 to the n, leave space, u of negative, I don't have enough room there. Hold on. Negative 10 times 0.9 to the n, u of negative n minus 1, except, I'm going to rewrite that. What do I have to do? I replace n by n minus 2 again, because it's z minus 2. So it's n minus 2, and I'm going to have to rewrite this down here because I don't have room. U of negative, by the way, n minus 2 goes in parentheses. We're replacing n by n minus 2. Didn't matter up there, but it does matter here. So that is actually u of negative n plus 2 minus 1. So negative 2
Yes.
plus 1, right?
Yes. Yes.
Plus 1. Okay, so there's the answer. This should be u of negative n plus 1. Not that. Gets a little tricky there, but the technique is exactly the same. Just remember, when you replace n by n minus 2, generally it needs to go in parentheses. Sometimes it won't matter, but there are times like this when it does. Okay. Tell me something. Is that up there causal? ROC goes to infinity? Is that causal?
Yes. If it's
N minus 2, N minus 2? Yeah, it starts at time 2 and goes to the right. Yeah. Is it well behaved? ROC includes who?
Use a circle.
Unit circle. Does it? Yes? Is it well behaved? Decaying? Decaying? Yes? Well, what about this one? Is it causal? Should not be, because it doesn't go to infinity. What part of that? Is there some part of that that's non-causal? U of. Okay. Where does that start? 2 and go to the right. Where does that start? 1 and goes to the left, non-causal?
Yeah,
Agree?
not causal.
Yeah, it's not. This one's non-causal. What about well-behaved? Is it well-behaved? Should it be? Unit circles out here. Not well-behaved? Doesn't include unit circle. Okay. Is there anything about that that's not well-behaved? This one right here, this 0.8 decays right like that, doesn't it?
Yeah.
What about that one? 0.9, and it's going that way. If 0.9 decays going to the right, but as it goes to the left, what does it do?
It's increasing.
Explodes. Not well behaved?
No.
Not causal? Yeah. Right, neither one. Because it doesn't go to infinity, it doesn't include the unit circle.
Yeah, yeah. No causal.
Okay? Now, yeah, that's what I was just kind of clearing up some final ideas there. And I want to spend about another 15 minutes. Can y'all deal with that? And I'm going to talk about transfer functions, and I'm going to talk about stability. And before I finish today, I'm going to talk about frequency response. Okay? So if I do this, y of n plus 1/2 y n minus 1 equals 3x of n. Simple little what? First order linear constant coefficient. What kind of difference equation? The main category, what is it? It's either this or that, and which is it?
Or it's recursive.
It's recursive, right, it's recursive. And so our transfer function is h of z would be 3 over 1 plus 1/2 z to the minus 1, or 3z over z plus 1/2. Right? How do we know it's recursive? Because there's more than one y of n term in the difference equation. What does that also correspond to? The transfer function has a denominator, right?
Yeah.
What happens if there's just one y there? Then you just have a numerator in your transfer function. Okay, so where are the poles of the system? At z equals what? Poles at the what?
RC.
Tell me.
Minus
Y'all.
1/2.
Negative 1/2? Right? Okay, so in this case, if we were to pick for an impulse response, then x of z equals 1, and y of z is just h of z times 1, which is just h of z. And h of n is what? If y'all tell me what the impulse response for that would be. Oh, no, you can't tell me what the impulse response for that would be. And there's a reason for it. Because you don't have a region of convergence. H of z does not come with a region of convergence. But if I plot its pole here, the pole is right there. Okay, I need an ROC. How many possible ROCs are there? 2, right? Where are they?
Inside, outside, outside.
Inside and outside. Okay, so I'm going to choose ROC. Ben, since you answered, I'll let you pick. Which one?
Outside.
Outside? Greater than a half?
Yeah.
Okay, which means, what do we have? We've got first case over there, top, right? And it would be negative, 3 out front times negative 1/2 to the n u of n. How do you feel about that one? Good impulse response? Yeah, why do you say it's a good impulse response?
Decays.
Decays, right? It goes 3 and then I think it's negative 3 over 2 and then positive 3 over 4 and negative 3 over 8. Is that right? It decays. What you said it decays. Why is that good?
Doesn't explode.
Go
It's
ahead.
well behaved.
Yeah, it's well behaved. And that means, since it's an impulse response, a decaying impulse response like that means that it is stable, right? System stable. What else about it? Where does it start?
0.
0, and what does that mean? This system is
Causal.
causal, okay? Stable and causal. Stable and causal. Well, that ROC is out here, and the unit circle is there, and that's a good thing, right? And infinity is out there. So, could we also, we have an h of z is 3z over z plus a half. Could we also choose a region of convergence less than a half inside? We could, couldn't we? But if we do, h of n is negative 3 times negative 1/2 to the n u of negative n minus 1. What do you think about that one? Where does it start or end, and which way does it go?
Goes to the left.
Yeah, it goes to the left. Starts over here, negative 3. I think
That's incorrect.
looks something like, no, doesn't.
Correct.
Right?
Yeah.
It's still the negative 1/2 to the n like it is over there, but negative 1/2 to the n going to the right is decaying, going to the left it's exploding. What are you saying? Non-causal? Non-causal? Stable?
Anti-causal.
It's also
Anticausal.
anti-causal. You're right. Non-causal and anti-causal. It's also unstable, isn't it?
Mhm.
Remember, take the absolute value of that and add them all up. It's going to blow up. Okay. Yes, you can choose the region of convergence either place, but what? You would never do this. Okay. Technically, you can, but no, we don't do that. Let me say it this way. Mathematically, those two solutions, one's just as good as the other. From an engineering perspective, no, they're not. That one's causal and stable, and that's good. This one's non-causal and unstable, and both of those are bad. Okay, so let's do the following. Let's talk about a problem and then don't do it. How about that? Does that sound like a good plan? Just talk about a problem and then don't solve it. What if I had this? H of z, I'm going to give you a system, and there's the unit circle, and I'm going to say that's pole there, pole there, pole there, pole there, and maybe a couple of zeros there or something. So I'm going to say h of z is, in the denominator, let's say z minus 0.9, z minus 0.8, z squared minus 2 times 0.8 times cosine pi over 10 z plus 0.8 squared. You recognize that form? And then let's just say like z cubed up here. 3 zeros over here. Only thing that's really important is that this is what order system? How many z's do you see? In the denominator,
4.
z squared 4. Z squared times z is going to be fourth order. And you may recognize this. This would give you poles at 0.8 e to the plus or minus j pi over 10. But again, not that important for what I'm going to do. What if I were to say this? My input to this system is x of n is u of n plus cosine of pi over 5 n u of n, pi over 5n, plus sine of pi over 2n u of n, plus sine of 0.8 pi n u of n. Okay. And the question, the problem I have for you is to find y of n. We actually know how to do this problem, but I doubt any of you are going to volunteer to do it. And my perspective is, as engineers, you shouldn't volunteer to do that, because that's a very difficult problem. True? It's not, in terms of difficulty, it's not horribly difficult. In terms of a nuisance terms, it's a real nuisance. You get a second order Z transform there, don't you? Remember that? You get a second order Z transform there. Second order there, and that was first order. So what we got? 2, 4, 6, 7. Once you find all those Z transforms and then you add them together, you've got a 7th order Z transform with 6 complex poles and 1 real pole. Okay? All right, so here's what you're going to do. Find x of z, then y of z is h of z times x of z, and then y of n is z inverse y of z. Well, the problem is really right there. What is the order of that? What did I just say the order of x was? 7? What's the order of h? Y'all have already told me.
4.
4? So this is of order 11. And most of the poles are complex. You've got, let's see, 1, 2, 3 of them. 8 of them are complex. 4 complex conjugate pairs. That's not going to be fun. And even with MATLAB, it's going to be a nuisance. So, what am I suggesting? I am suggesting this. If you're only interested in what happens in the steady state, you remember the response has always got a transient part and a steady state part. If you're only interested in the steady state, there's a much better way of doing that. Okay? And that is using the discrete time Fourier transform. And that's the topic for Wednesday's lecture.
Discrete time?
All right? So we're going to start talking about the discrete time Fourier transform on Wednesday. Homework. Y'all be working on that. Tell me when you want to turn it in. You have homework to do today?
Well, we got to finish just the plotting part.
Oh.
So
okay.
that'll be done
All
for
right,
next
yeah,
class.
do that and turn it in Wednesday. And I will try to find homework number 2 because I think it escaped my office. No, actually, I thought I found it. It's on my hard drive. It's just that I thought I'd already given it to you.
So we turn on the homework one on
Yeah,
Wednesday?
do the MATLAB part and turn it
Okay.
in on Wednesday.
All right.
And let's say some of this, start working on this at least, number 3 and 4 and 5 and whichever ones. All right?